Blaise Pascal, the source of everything that is wonderful about not having to do algebra in order to get solutions to algebraic situations. All right, so it's kind of a little bit of a lifesaver, an incredible lifesaver. It's very nice. All right, so let me just kind of walk you through the basics of it first, and then I'll do one of the examples for you so you get a good feel for it. Right. So what this triangle is telling us is the result of the coefficients, or you have an expansion of binomials, and when you expand those binomials, you have a set of coefficients. These are those coefficients. All right. So if I take the binomial, I'll just use the generic x plus y and raise it to the 0th power. The result is going to be equal to 1 because anything to the 0th power is equal to 1. All right, so that part's easy enough. Now, if I were to take x plus y and raise it to the 1st power, I would get x plus y, which is not 1 and 1, but the coefficient of x is 1, and the coefficient of y is 1. So that's where those numbers come from. All right. If I were to take x plus y and raise it to the 2nd power, I won't bore you with the details, but the expansion here will be x squared plus 2xy plus y squared. Coefficients 1, 2, and 1. All right. So we do it for the first few cases to get a sense of how it's working, why it's working. But then after that, we say, well, there's a reason why we have this triangle. I don't want to do this to the 3rd power. I definitely don't want to do it to the 4th, 5th, 6th power. It's going to be a nightmare. All right, foiling or double distributing two binomials, not too bad, but throwing another one after that, another one after that, it's a nightmare. All right, so we can survive with just doing it for a few cases to get a sense of how things are going, and then after that, we rely on the trend. All right, so that's the idea. So now if I needed something like x plus y to the 5th power, actually, you know what, I'll jazz it up a little bit. I'll say x plus y to the 6th power. I'll do it underneath. Well, the first row is the 0th power. The 2nd row was the 1st power. Then the 2nd. Then after that, we'd have the 3rd power, the 4th power, the 5th power. It turns out that the 2nd entry in each row corresponds with the power. All right, so that's a kind of nice way of keeping track of things. But you can always just count rows too. You just got to remember that that first row isn't really the first row; it's the 0th row. All right, the pinnacle of the triangle is really the 0th row. All right, so we need one more row. So how do you go from row to row? Well, each row starts and ends with a 1, and then every consecutive value gets added to give you the entry directly below. All right, so if I take the 1 and the 5 here, I'll get a 6. The 5 and the 10, I'll get a 15. The 10 and the 10, I'll get a 20. 15, 6, and 1. All right, so now I have all the coefficients of x plus y to the 6th power. Great. But how does that help me get something like what we got when we expanded out x plus y to the 2nd, x squared plus 2xy plus y squared? I don't have the x's and y's. I need those. So I'm going to put in my coefficients. I'm going to give some space because I need some x's and y's in there. So 1, 6, 15, 20, 15, 6, and 1. I'm done with the triangle at this point. A little bit more room for that last one. All right. Now, if you look at the cases that we did expand, when we raised it to the 1st power, x started off with the power of 1. when we raise it to the second power, x started off with a power of 2. So if I raise it to the 6th power, x is going to start off with a power of 6. And then it's going to decrease from there. So x to the 6th, 5th, 4th, 3rd, 2nd, x to the 1st is just x, and x to the 0th would go away. All right? Now the same thing happens for the y's, but in the reverse direction. Right? In the first case, well, in the case of x plus y to the 1st, the last term had y to the 1st. In x plus y to the 2nd, the last term had y to the 2nd. So in x plus y to the 6th, the last term is going to have a y to the 6th. So I'm going to throw that in there. I'm going to go red for those keeping score at home. So y to the 5th, 4th, 3rd, 2nd, 1st, and 0th. 0 is going to zap away. Y to the 0th is 1. All right. Now, the binomial is completely positive. If you multiply two positives, you're going to get positive. There's nothing about that expression that suggests that your result will be anything other than positive. So I'm going to chuck some plus signs in here. And you could ditch the little 1 here. Oh, I'm locked out of erasing it for some reason. Oh, because I wrote it out of sequence. I'll just leave it. But you could ditch the 1s. You know, you don't need 1x to the 6th, 1y to the 6th, but you could leave them in there too. I was going to say nobody ever took off credit for something like that, but I'm sure somebody has. I've never taken off credit for having 1x to the 6th as opposed to just x to the 6th. All right, so that's the full-blown expansion of x plus y to the 6th. Now, if you imagine what you would have to do if you didn't do that, no, pen turned off. Or you'd have to take x plus y, multiply it by x plus y. We already know that's x squared plus 2xy plus y squared. But then you'd have to take that and multiply that by x plus y, get that answer, and then do the process 3 more times. Yeah, that's like the rest of the school day, I think, to do it. Well, probably like the rest of the class period to do it, the rest of the school day to try to figure out where you screwed up. Because so much algebra in there, you know, it's a mess. All right, now, the extension on this is like, okay, well, this is all x plus y, and you're very, very well versed in x plus y now. And then you look at all the examples, and not one of them has an x plus y in it. So you're like, okay, now what? All right, so let's take a look at, well, we'll do B, I guess, because it's fairly juicy. Now, every one of them has an x plus y, but it's not necessarily represented as x and y. So this is my quote-unquote x, and this is my quote-unquote y. I regret circling it in blue. All right, so Pascal is going to give you the coefficients for the expansion. We know it's power of 3. So 1, I did not turn my pen on. I thought I did. Where did my pen go? 1, 3, 3, 1. So I'm going to take my x term, my quote-unquote x term, start it off, raise to the 3rd power, decrease the exponent by 1 consistently until you run out of power. So x to the 1st, x to the 0th goes away. All right. Then I'm going to take my negative 3, bring that at the end. That's my y term, my quote-unquote y term. I'm going to raise that to the 3rd power on the right-hand side. Dial down the powers as I go from left to right until I run out of power. The very last entry should have it disappearing because negative 3 to the 0th power is going to go to 1. So it's a factor of 1. It's the identity element. All right. So then just like the other ones, I'm going to chuck plus signs in it. And you say, wait a minute, there's some negative signs here. Yeah, that's going to come out in the wash because I have the -3 built in here. In some cases, it's going to be positive. In some cases, it's going to be negative. All right, so now I just need to simplify a little bit. The first term, x cubed. The second term, I got a 3 times a -3, so -9 x squared. The third term, I'm going to go purple on that one. I have a -3 squared, which is going to be what? Positive 9 times the 3 that's already there, 27x. And then I just need to raise -3 to the third power, and I get? -27. All right, and that's your full-blown expansion. If you're in doubt, your calculator is very helpful for this because, and tomorrow it'll be even more helpful because I'm gonna dump programs into your calculator. So if you have a graphing calculator at home, bring it in tomorrow and actually start bringing it in. And if you haven't gotten one yet, try to get one as soon as you can because I have programs that I'm just gonna give you. One of them is called PreCalc, where you type in these coefficients and it gives you the full-blown expansion. All right, so it's going to do all this for you, but I'm a firm believer in the idea that I don't want you using a tool unless you know how the tool works. All right, you got to be trained in proper usage of said tool. All right, otherwise it's just a tool. So how to check? Put the original expression in, x minus 3. Raise it to the third power. Put your newfangled expression in. Now, if you have like the old school one, like I do, the black and white, no color, you don't mess around with color. Just go straight with those AAA batteries. No recharging around here. If that's the case, then what you want to do is hit enter on that little slashy thing over there, which I believe is called the slashy thing. All right, if you have one of the rechargeable color ones, then it already distinguishes one graph from another, so it's fine. But I need to be able to distinguish one graph from another, otherwise, if they're mapping to the same location, I won't necessarily know it because I might think one graph is coming up on the screen and maybe one is off screen. They're not even remotely the same. Here it's going to verify very nicely that they are in fact the same. So I'm just going to do a zoom 6, right? Standard zoom. That's your -10 to 10 all around. Original, extra crispy. And there it is. All right, now you don't really actually have to look at the graph. You can go to the table and see, but it's not as satisfying as that. It just feels nice when you see it like that. It's like that moment of suspense, hesitation, pause, like did I do it right? And then it happens, and then you go, yes. And then you realize you just said yes in front of a bunch of people over a math problem, and then they think you're like a lame-o, but it's all right, you'll get over it. Right, so that's Pascal's triangle in 14 minutes. All right.